Okay, so in this unit we'll be looking at digital signatures and digital certificates and digital signatures. And basically what we have is that Bob has a public key and a private key. Okay, he keeps the private key secret. And then what he'll do is that when he wants to sign for something, he uses his private key, and then he can prove that with his public key. So the problem that we have is that how does Alice get Bob's public key without, so that she knows that it isn't a fake key? For this, we use a digital certificate. So a digital certificate can hold the public key and the private key for Bob. And it's basically signed by a trusted entity, Trent in this case, or Megacorp. But the certificate which is distributed only has Bob's public key on it. And because it's signed by Trent, then Alice can trust the certificate and thus can trust the public key. Okay, so we'll have a look at how digital certificates are used, then some authentication methods, go into public key infrastructure, or the PKI, passing certificates, and then also onto some digital signature methods. Okay, so we should all be used to seeing the little green bar to identify whether we have a secure connection. It is here that we can interrogate the public key of the entity to make sure that it's been signed by a trusted source. It is this key that thus identifies the server. And after this, we can make sure that we have a secure tunnel between the client and the server. Okay, so what we really want to do is to make sure that we authenticate our devices, our users. We need to keep things confidential, and we obviously need some integrity there within our infrastructure. Okay, so the problem that we have is that how can we get the public key from Bob to Alice without Eve pretending to be Bob and saying that she is passing Bob's public key? And how can we make sure that something hasn't been tampered with between Bob and Alice, for example, where Eve becomes an Eve in the middle? So how do we make sure that the public key is sent to Alice, even though Bob is offline whenever Alice needs to use the public key? And really, can we trust Bob himself to sign his or distribute his public key? For that, we turn to Trent, and we need Trent to make sure that Alice receives the public key in a trusted way. Okay, so let's look at some authentication first before we go on to look at digital signatures. Overall, we authenticate lots of different things on the network to make sure they're trustworthy: users, data, devices, systems, and so on. And for this, we either have end-to-end authentication, where we authenticate the user, Bob, to the service, or we can have intermediate authentication, where we will authenticate a device to a server. The best method is obviously end-to-end authentication, but sometimes we can't get that, so we will often go for an intermediate authentication. So Bob owns a device and a service is running on a server, so it was mostly authenticated there, but obviously there's an opportunity for Bob to lose his device and for the service to be replaced by another one. So in most cases, end-to-end authentication is the best. And when we're authenticating, we can either pass our identity from the server to the client, or the client to authenticate themselves to the server, or mutual authentication on either side. This is typical on the web for HTTPS, where the user doesn't really provide a certificate of their identity to the server, but the server provides that to the user. Sometimes in a wireless network, we need to identify devices. So for that, we can use EAP-TLS to pass the certificate to the server, or to be able to sign some data from the client to the server. And in some other cases, such as in PEEP, pure PEEP, we need authentication on either side, where the identity or the public keys are passed either way. Okay, so there are many ways that we can identify a device or a user. There's usernames and passwords, of course, a digital certificate, soft tokens, biometrics, and so on. The devices might be identified by the MAC address, encryption key, and so on. So we typically define the areas of authentication are something you know, something you are, and something you have. We can also include somewhere you are. So this can provide information about your location. But normally with multi-factor authentication, we want to be able to pick off one, two or more of the different areas. It doesn't do much good to pick off all of the authentication methods in the one area. So we will typically mix and match with something you know, with something you are, or something you have. So for something you know, obviously username and password, your mother's maiden name, and so on. For something you are, that typically is around biometrics, such as retina scans, iris scans, palm prints and fingerprints. And for something you have, it might be a digital certificate with a private key, a network address, or a smart card. Okay, so now let's look at digital certificates and how they are used to pass the public key. Okay, so we need a way to be able to get the public key from Bob to Alice so that Eve doesn't get involved with it and change any of the details. So when we view a certificate, we can view it graphically, and it will typically tell us who it's issued to, who issued it, and when it's valid. We can then view some of the parameters on the certificate, such as the public key. The thumbprint gives us the signature. So the issuer takes a hash of the digital certificate, and then will sign that with their private key. And of course, there's the issuer, which is fundamentally important to the trustworthiness of the certificate. So there are two different certificates that we might get. One only has the public key on it, such as this one here. Okay, just the public key. And the other one actually has the private key on it. So this is the one that we want to keep secret. So this one here has both the key pair on it, and we wouldn't really release that. Okay, so before we do that, we'll have a look at an example certificate. Okay, so we're connecting to Google here. So let's have a look to see if we can view the certificate. And here it is here. Okay, so there is the common name for the certificate, and here is who's issued it, and there is the date for the validity. So those are the top level details of the certificate. We then get the information about the public key. So in this case, it's an elliptic curve public key, P256, and here is the public key value if we need it. There's a serial number, and it tells us what the signature is on the certificate. So this will be the signature here. The issuer will take a hash of the certificate, in this case was SHA-256, and then will encrypt with their RSA private key and create the signature here to validate the the certificate. Okay, so here we are. Here's the fingerprint using SHA-256 and SHA-1 also. There's a ID for the certificate and a few other details about the certificate there. Okay, so those are the basic details that we'd have in a digital certificate. Its name, how long it's valid for, any alternative names, the public key itself, the signature method on the on that, and we can also export the the public key if we need to in a certificate form from here too. Okay, so we'll come back on to the trustworthiness of this in a little minute. But there are several formats that we can have for these things. There's the P7B format, and hopefully you should be used to this format. It has begin certificate and end certificate at the end, and then we'll get base 64 in between. This is a text format that we can import into our system as required. We can also get a PFX or a P12 format, which is a binary format, and with these we can actually apply a password onto the certificate. So this would typically be when we need to protect our private key. Okay, so let's step through a basic flow using public key encryption for both encryption and also for signing. Okay, so Bob sends a message, Alice sends her certificate over with her public key, then Bob can encrypt that with her public key, and then she'll decrypt it with her private key. What we can also do is we can take a hash of the message, and we can take Bob's private key and sign the hash, send it over, and then Bob will send through his public key on a certificate, and then Alice is able to check the signature against the hash of the message with his public key. Okay, so here is an example of a certificate. As we saw before, we can see that the basic details of the certificate, who issued it, and how long it's valid for. There is then also a certification path for the certificate. And the way that we create the certificate is that we will generate a key pair. In this case, we're generating 2048-bit RSA key pair. We then create a code signing request. With this, we will extract the public key and send that as a code signing request to a root CA. The CA is a certificate authority, and it will then create a certificate using its own private key to sign the certificate. Okay, so we generate the certificate here, and then we sign it here. This then creates a CRT file here, which can then be sent back to the organization as a certificate for the organization. In this way, the root CA has signed the certificate with its private key, but they only get the public key, and the public key is contained within a container. One of the most popular CAs is now Let's Encrypt. So they now have root signing, and as we'll find, they can also have intermediate signing. And the good thing with Let's Encrypt is that it is free of cost, where other CAs will charge often for the creation of the certificate. Okay, so here's the PM format that we can have, or we can have a PKCS7 format, which is this type of format here. Both are typically able to be read by our systems. And then we have two formats for our certificates. One is a DER format, and that is defined in a binary as a binary form along with a SER file. So these are some of the commands here that we might use to be able to export our keys. Okay, so how do we make sure that we can trust Bob's certificate? For this, we need Trent. So let's go through an example here. Bob contacts a trusted root certificate authority, and Bob's identity is checked. The trusted root CA will send through a certificate with Bob's public key, and it'll be signed by Trent. Trent's root certificate is installed on Alice's computer here. So this will contain Trent's public key. So when Bob sends through the certificate with his public key, then Alice will check the signature on the certificate against Bob's public key here to make sure that it was Trent that signed it. But unfortunately, Eve might trick the CA into pretend to be Bob, and she could get a valid digital certificate if the Trent hasn't checked, and everything will look okay. So we need to watch out for this because someone could spoof a certificate. So what we have is different levels of trust on the PKI or the public key infrastructure. We have root signers who are always trusted for everything that they do. These public keys are installed by default into the operating system, and we need to watch that we don't get malicious root CAs in there. We then have an intermediate CA, and they can sign for various applications such as for Windows drivers or for email or for an IP tunnel. And they're only trusted within inside those services. Then finally, there's a self-signed certificate which can't really be trusted and is typically only used on development environments. Okay, so let's have a look at some here. So let's not include the fact that the certificate is timed out. We need to see if this is valid or not. And actually it looks quite valid, and when we check the certification path, we can see it goes right up to the top here. If we go back to our example earlier, we should be able to see in Google's case what the intermediate signer is here. Okay, so we can see here Google Trust Services, and there's the public key information and so on. And then that should go right up to the top to give us a root CA, which is a top level CA for the trustworthiness of these intermediate signers. Okay, so this one, it's not good, it's self-signed. We should find that when we try to use this one, it will say to us, do you want to import it? The last thing that we should do is to import this type of certificate into a root authority, because it would give that authority high levels of trust on the system. In this one, we have a wildcard, which isn't really a very good mechanism, and it's generally protecting lots of different services without locking them down. So it is real, and it will go right up to a root CA. Everything looks fine on there. Okay, so now let's look at stepping through the basic process that we have for passing certificates. Okay, so Alice sends her public key. For that, she'll send the certificate. So she'll have a certificate that will have her public key on it, and she'll send it over to Bob. Bob will then take the message and then also a hash of the message and add his signature with his private key. And then he'll take Alice's public key and send that over, all encrypted. Alice will then take her private key from her certificate and is able to decrypt the message, and she's left with the signature. Then she takes Bob's public key and proves the signature was from Bob. And she knows that Bob sent it and also that it hasn't been modified. So let's step through that. We take the message, take a hash of the message, and then we can take Alice's public key. We can encrypt the whole message. Alice gets it, she decrypts with a private key, and then checks the hash of the message for the signature using Bob's public key. Finally, let's look at digital signatures, because what we need is a signature on our certificate to make sure it's valid and it's been signed properly. So for this, we have a key pair, and the most popular signature methods that we can have are ECDSA, ECDSA, RSA, and DSA. Normally these days we use RSA or ECDSA, but increasingly we're also using ECDSA. For this, we normally generate an R and an S value for the signature. It is those two values which is used to verify the signature. So how does Trent get involved with this? Well, Trent will actually sign for Bob's private key. So in this case, Trent will export his public key onto what's called an X509 certificate. This is a certificate that Alice has. And when Alice receives Bob's public key on a digital certificate, Alice will check it against Trent's public key to make sure that the digital certificate checks out. So this is the mechanism for ECDSA. I won't go into the detail there, but basically we create a random nonce value k for every signature. We take the private key and we take a hash of the message and we create values of R and S. Then Alice takes a hash also, takes Bob's public key and R and S, and is able to prove the signature or not. RSA signatures are different because we use the private key, then we take the message to the power of D, the decryption exponent, mod n, and then on the other side we can do a check to get the original message back by taking the signature to the power of E, mod n. It's just basically the opposite operation to an encryption process. Finally, SNOR signatures are now being used extensively, and they are much more simple than the ECDSA method that uses elliptic curves. For this, we can actually aggregate the signing process much easier, and this gives us much more applications in this modern world. I won't go into the detail here, but again, we produce an R and an S value, and then we'll be able to check that against the signature. This uses an elliptic curve method, as does ECDSA. Okay, so that's been a coverage of digital certificates. Thank you.